So in this video, video 5, we're going to find the equation of a quadratic function using the graph of the parent function x squared and thinking about the transformations that have been applied to the toolbox function x squared to create the new function. So in this case, we're given a graph that's a quadratic function, and we want to recognize that the toolbox function is just the squaring function, and we want to identify what are the transformations that have been applied to the toolbox function in order to create this new function that we see on the screen. So first thing, we know we've got nice lattice points, and we notice the scaling on the vertical axis is counting by twos. So the lattice point would really be located at 0, 0, and 1, 1. I need to be careful not to put the point on the lattice point here, thinking that this is a 1. So we have to identify that the scaling on the vertical axis is not what we would typically expect. And now we think about what are the transformations that have been applied to the function. Well, this origin, the vertex, which is located at the origin for the squaring function, has been moved 1 to the right. Right? The squaring function usually comes up and does this type of a thing. So the vertex has been moved over 1 to the right. So we are moving horizontally right 1 unit. And then we think about, are there any reflections going on? Well, no, the squaring function opens upwards. The function we have opens upwards. So no reflection has happened. And it doesn't make sense to talk about reflection over the y-axis because our parent function has symmetry. So we know that there's no reflection going on. And we can think about stretch. Is there any stretch going on? And so usually the squaring function goes over 1 up 2, over 1 up 1, but we can see here it goes over 1 up 2 because there's a factor of 2 between points on the vertical axis. So it looks like we have a stretch by a factor of 2. And then 4, is there any vertical transformation going on? Well, yes, the origin's not only been moved 1 to the right, but it's been moved down 10 units. So it's been moved down 10 units. And then we build our function using that information. So we get the function f of x equals, we need to shift it right 1 unit. So that means subtract 1 from the input variable. There's no reflection and no stretch, there's no reflection, but there is a stretch by a factor of 2. So a times 2 multiplier, and then down units means subtract 10, and now we have a function that is in vertex form. It's just as a reminder, if we're uncomfortable finding the stretch by looking at the graph, or if the stretch isn't nice, we can always take a point on the graph, a known point, and figure out what the stretch is from there. So what I mean by that is, if I don't know what to put here for the 2, I just take the function f of x equals, I go a times, and I have x minus 1 squared, x minus 1 squared minus the 10. We just put an a there and we say, hey, I don't know what the stretch is. Or I'm not quite sure. I trust myself to just eyeball the graph and get the stretch. And then you grab the point and you put that information in. This says if the input's 3, the output's negative 2. So replace the output with negative 2. Replace the input with the 3. And then solve. So I'm going to add 10 to both sides. So I'm going to get negative 2 plus 10 equals a times 3 minus 1 is 2. 2's being squared. 2 squared is 4, so I get a times 4. Negative 2 plus 10 is 8. Get a by itself by dividing both sides by 4, and that gives me 2 equals a, so we replace the a with the 2 that we see right here. And that's how we get the equation of our function using the graph.